Welcome to the lecture series on organic nitrogen compound. This is episode 4 in which we are going to introduce amines. We will discuss their nomenclature and physical properties also. In the earlier episode of organic nitrogen compounds, we have discussed nitroarenes, that is the compounds where nitro group is attached directly to the aromatic ring. We had discussed their preparation and their chemical properties in detail. We had discussed various reactions where, because of the presence of nitro group, the alkyl group present on benzene ring could give a number of condensation reaction, thereby forming a number of very important class of organic compounds. In the present lecture, we will discuss amines, the classification, we will discuss some biologically active amines, we will discuss the nomenclature of amines in detail, and after that we will discuss salts of amines, we will discuss physical properties like boiling point and solubility of amines. We will then discuss the structure and stereochemistry of amines. To start with the introduction of amines, amines are the nitrogen containing organic compounds having NH2 function. They are structurally related to inorganic ammonia and are basic in nature. You already know that the formula of ammonia is NH3. If we replace one of the hydrogen from ammonia, then there is formation of this NH2, that is the functional group amine. And ammonia is basic in nature, similarly amines are also basic in nature. They are called derivative of ammonia, in which 1, 2 or all the 3 hydrogens of a hydrogen atom are replaced by alkyl group or by aryl group. If one of the hydrogen is replaced by alkyl or aryl group, the amines are named as primary amines. In case 2 hydrogens are replaced, they are called secondary amines, and if all the hydrogens of ammonia are replaced by alkyl or aryl group, then they are called tertiary amines. Here you can see with this example that this is ammonia molecule. Here the nitrogen is attached to 3 hydrogens. Now, if one of the hydrogen is replaced here, then there is formation of primary amine. If 2 hydrogens are replaced by alkyl groups, then there is formation of secondary amine, and if all the 3 hydrogens of ammonia are replaced by alkyl group, they are called tertiary amines. They are categorized as primary, secondary or tertiary amines depending upon whether nitrogen is joined to 1, 2 or 3 alkyl or aryl groups respectively. That is, one type of classification is that alkyl group is replacing hydrogen. The other way we can say that 1 alkyl group is attached to nitrogen, or 2 alkyl groups are attached to nitrogen, or 3 alkyl groups are attached to nitrogen in case of primary, secondary and tertiary amines respectively. Another class of compounds besides primary, secondary and tertiary amine is quaternary ammonium salt, and in these salts nitrogen is a quaternary function, that is joined to 4 alkyl groups. You can see here in this example that this is ammonium salt. If you are asked to name this molecule, this basically is ammonium halide. Now, if all the 4 hydrogens of this ammonium group or ammonium ion are replaced by alkyl group, then there is formation of this salt. This is called tetrahedral ammonium salt. So, another class of compound having nitrogen as functional group are quaternary ammonium compound, where all the 4 hydrogens present in the ammonium salt are replaced by alkyl group. The amines are also classified as aliphatic cyclic amines. Aliphatic cyclic amines are those amines in which nitrogen function is a part of cyclic ring. Like in this case, you can see that this is a 6-membered ring, where one of the member of 6-membered ring is nitrogen, and here in 5-membered ring nitrogen is a member of the ring. A 6-membered ring containing nitrogen is named as piperidine, whereas a 5-membered ring is named as pyrrolidine. So, this class of nitrogen containing compound or amines basically are called aliphatic cyclic amines. Then another class of amines is aromatic amines, wherein the NH2 function is directly attached to aromatic nucleus. The aromatic amines can be classified into two classes. One is aryl amine and another is aromatic heterocyclic amines. In case of aryl amines, the nitrogen atom is bonded or amino group is bonded to one or more aryl groups directly. Like in this case, you can see this is amino functional group which is attached to a benzene ring, aromatic ring, and the name of the molecule is aniline. Here this nitrogen function is attached to two aryl rings and the name is diphenylamine. This again comes in the category of aromatic amines. Here in this case, all the three hydrogens of ammonia are replaced by aryl group. That is why the name is triphenylamine. Another class of aromatic amine is aromatic heterocyclic amines. Here the nitrogen is a part of aromatic heterocyclic ring. For example, in this molecule, this is called indole, this is pyridine, this is pyrimidine, pyrrole and imidazole. All these rings are aromatic in nature and they all have nitrogen as a function. Another class of amine is alkyl amine or also called aryl alkyl amine. Here you can see that there is an aryl nucleus and amino group is not directly attached to the aryl nucleus, but it is attached to benzene ring via a carbon, and that is why this is called aryl alkyl amine. The name of the molecule is benzyl amine. We will now discuss some biologically active amines. You will find that amines are a class of compound which are actually very interesting, and some of the very interesting molecules contain nitrogen as amino function. For example, in case of neurotransmitters like dopamine, this contains amino function. Then bioregulators like epinephrine also has amino group. Vitamin B6, which is also called niacin, contains amino group. Alkaloids like caffeine, nicotine, morphine and cocaine, they all have amino function. Amino acids, you know, are a very integral part of our body or our living system, and they also have amino group. So this class of organic compounds, the amines, are very interesting and very important for the life to be present on this universe. Here we have some of the examples of molecules which have amino group and which are biologically active. For example, you can see dopamine. This dopamine is a neurotransmitter, as we have earlier told you. This epinephrine is an adrenaline hormone. This is L-tryptophan, which is an amino acid. Piperazine is the molecule or the reagent which kills intestinal worms. Nicotinic acid or niacin is a vitamin. Pyridoxine is vitamin B6 and histamine is used as a blood dilator. We will now discuss caffeine in detail. You may find it interesting that caffeine is a part of a number of drinks which all of us are consuming in our day-to-day life. Caffeine is a bitter alkaloid found in coffee, tea, cola beverages and chocolates. It is a mild stimulant and it induces a feeling of alertness after its consumption. It also increases heartbeat, dilates airways and stimulates the secretion of stomach acid. Excessive use of caffeine can result in insomnia also. Cocaine, another biologically active amine, and amphetamines are several other addicting drugs based on amines, and they increase the level of dopamine in brain, which causes pleasurable high. With the passage of time, the brain adapts to the increased dopamine levels, so more doses are required to produce same sensation. They are therefore addictive drugs. This is dopamine and this is epinephrine. We will now discuss the nomenclature of aliphatic amines. In aliphatic amines, the nitrogen atom is bonded to 1, 2 or 3 alkyl groups, and in the common system of nomenclature, the aliphatic amines are named by using prefix for the alkyl chain or the group followed by the word amine. In this particular example, you can see that nitrogen is attached to one methyl group and two ethyl groups, and that is why the name of the molecule is diethyl methylamine. In this particular case, this nitrogen function is attached to one methyl group and the other is cyclopentyl group. Hence, the name of the molecule is cyclopentyl methylamine. This is the common system of nomenclature of aliphatic amines. In case of naming of these aliphatic amines, name the alkyl group bonded to nitrogen first and then add suffix amine. This is what we had done in earlier case also. Here you can see this is dimethylamine because nitrogen is attached to two methyl groups. Here, since nitrogen is attached to 3 methyl groups, it is trimethylamine. But if the alkyl group attached to nitrogen are different, then they are named differently and that too in alphabetical order. For example, here this is the methyl group and this is ethyl group. Now, E comes before M and that is why first we will write ethyl and then methyl, and after that the suffix amine is added. So, the name of the molecule becomes ethyl methylamine. See here what happens. This is a primary amine, and how are we going to name this molecule? Because here the amino function is attached to this carbon and this is one alkyl group. So, we will actually see the nature of the alkyl group. If you look at this, this contains 4 carbon atoms. So, the alkyl group is named in common system as secondary butyl, and that is why the name of the molecule becomes secondary butyl amine. The same molecule, when we will discuss in case of IUPAC nomenclature, will have a different name. You will see in the slides to come later. Here again you can see that this amine, this nitrogen atom or amino function is attached to 2 phenyl rings. That is why the name of the molecule becomes diphenylamine. Whereas in this case nitrogen is attached to 2 methyl groups and 1 benzene ring, and that is why we will name it as a function of aniline. Had there been 2 hydrogens, the molecule would have been aniline, and 2 hydrogens here have been replaced by 2 methyl groups. That is why the name given to the molecule is N-dimethyl aniline. We will now discuss IUPAC nomenclature of amines, and as usual the rules for IUPAC nomenclature are same as we have discussed earlier in almost all classes of organic compounds, and the name of the molecule is based on longest possible carbon chain in a molecule. That is, first of all we have to find out which is the longest possible carbon chain, and if the carbon chain has 4 carbon for example, then we will replace the E of that alkane with that of amine. That is, a 4 carbon alkane is butane, replace E and add amine. So, the name of the molecule will become butanamine. Substituents on nitrogen have N-prefix. For example, in this particular case you can see that the longest possible carbon chain contains 4 carbon. So, this is an amine with 4 carbon. So, we will write butanamine, that is replace E from butane and add amine after that. But butanamine will not be the complete name for the molecule, because you have to give the position of attachment of amino group to the main chain, and if we number it from here, position 2 will have amino group. If we number it from here, position 3 will have amino group, and if you recollect the IUPAC system of nomenclature, then minimum possible number is given to the substituent, and that is why the name of this molecule becomes 2-butanamine. In this particular case you can see that this is an example of primary amine. The amine is attached to the second carbon of 3 carbon alkane. If you number the longest possible carbon chain, you will number either from here or from here. If you are numbering from here, the number comes out to be 3, 1, 2 and 3. Whether you number from here, then also it comes out to be 3. So, what we will say that this is an example of, or this is propanamine, but which carbon of propane is substituted by amino group and which carbon is substituted by methyl group. If you look at carefully, you will see that position 2 of propane or carbon 2 of propane is substituted by an amino group as well as by a methyl group, and that is why the name of the molecule becomes 2-methyl 2-propanamine. Some more examples we will discuss here. You can see the longest possible carbon chain contains 6 carbons here, but if you number it from here, the carbon having amino group will have position 4. If you number it from here, the carbon having amino group will have position 3, and since according to IUPAC nomenclature minimum possible number is given to the substituent, the correct name of the molecule becomes 3-aminohexane. Here in this case, the case is a bit different because you can see that this alkyl group is attached to amino group. One of the hydrogen of amino group NH2 is replaced by methyl. So, we will name the molecule as N-methyl ethanamine. 2 carbon alkane is there. So, N-methyl ethanamine will be the name of the molecule. Here in this case, we have a secondary function, that is N-methyl group is there, but a hydroxy group is also there. And if you look at the molecule, you know that hydroxy group takes priority over amino group, and that is why the name of the molecule will be 2-N-methylaminoethanol. This will not be a derivative of amine, but a derivative of ethanol. We will now discuss another example. Here again you can see nitrogen is attached to 2 ethyl groups and 1 methyl group. So, the name of the molecule will be N-ethyl N-methyl ethanamine. That is, the 2 alkyl groups will be taken on nitrogen and the third one will be taken as main chain. Here N-methyl cyclopentylamine will be the name of this molecule. In this particular example, you can see that we have an amino group as well as a bromo group present in the molecule. Amino group takes priority over bromo group or halogen group, and that is why we will number the molecule from here. That is, the molecule will have a 3-bromo substitution and 1 amino substitution. Hence, the name of the molecule is 3-bromo 1-pentanamine. In this particular example, this is the amine. Actually, it is a tertiary amine where the nitrogen is attached to 2-methyl group. At the third attachment, nitrogen is attached to a 6-carbon alkane at position 3, and that is why the name of the molecule is N-dimethyl 3-hexanamine. When amino group is present as substituent over a high priority functional group, then NH2 is named as amino group. For example, in this particular case, we have 2 functional group, the amino group and the carboxylic group. Carboxylic group takes priority over amino group. Hence, the naming is done preferentially from carboxylic side. This carbon will get position 1, 2, 3, 4. So, the name of the molecule will be 4-amino-butanoic acid, or if you number them as alpha, beta, gamma, then alpha, beta and gamma. So, gamma amino butyric acid can also be the name of this molecule. Here in this case, this is 2-aminoethanol because hydroxy group takes priority over amino group. Similarly, in this case also it is 2-methyl aminophenol. Position 2 of phenol has methyl amino group, hence the name. In this particular case, this is a carboxylic acid, 3-carbon carboxylic acid is propanoic acid with position 3 having amino group, hence the name is 3-aminopropanoic acid. Now, regarding the nomenclature of quaternary ammonium salts, they again are named as per the alkyl groups attached to the nitrogen function. For example, in this particular case, nitrogen is attached to 4 ethyl groups. That is why the name given to the salt, quaternary ammonium salt, is tetraethyl ammonium chloride. Whereas, in this particular case, out of the 4 substitutions, 2 are ethyl, 1 is methyl and the 4th one is phenyl. The name given to the molecule is N-diethyl N-methyl anilinium bromide. Here you can see that we are adopting the alphabetical order, that is D comes before M, that is why the ethyl groups are named first before the methyl group. In this case, you can see that this is a quaternary ammonium chloride where only one hydrogen is replaced by a normal propyl group. Otherwise, all the three hydrogens are present as such, and that is why the molecule has been named as N-propyl ammonium chloride. We will now discuss the quaternary ammonium salts of amines. When aqueous mineral acid or carboxylic acids are added to amines, they form quaternary ammonium salts, which are readily soluble in water. You can see that this is a primary amine, this is secondary, and this is tertiary amine. When aqueous mineral acid is added into it, all of them are converted into their respective ammonium salt. The amines are insoluble in water, whereas salts are soluble in water. This property of solubility of quaternary ammonium salts in water is used for the separation and purification of amines very effectively from a mixture where there is no other basic reactant is there. We will now discuss some important physical properties of amines. The lower aliphatic amines are colorless gases, while those with 4 carbons or higher members are liquids. Methylamine and ethylamine have ammoniacal smell, but higher amines have fishy smell, and they are all lighter than water. Aromatic amines are generally very toxic, and they are readily absorbed through the skin and often with fatal results. Aromatic amines are very easily oxidized by air, and although most of them are colorless, in pure conditions they develop color due to oxidation in presence of air. Amines show polarity. Polarity means difference in the electronegativity. If you look at the NH bond in amines, the two atoms nitrogen and hydrogen have different electronegativity. As a result, NH bond in amine is polar in nature, and the overall molecule show polarity. This results in the formation of hydrogen bond with other amine molecules or other hydrogen bonding systems like water, and therefore, it is responsible for high melting and boiling points of amines compared to other analogues of alkanes of similar molecular masses. Also, amines have higher solubility in water. The reason remains the same, they can form hydrogen bond with water. You can see here that this is aniline C6H5NH2. Here at the nitrogen you can see a lone pair of electron. Because of the electronegative nitrogen, this nitrogen can attract the hydrogen from another aniline molecule because this is slightly electropositive in nature. As a result, there is formation of hydrogen bond, and this hydrogen bond results in the solubility of amines and also in having higher boiling points of amines. We will now compare the boiling points of alkanes, alcohols and amines. Like ammonia, amines are polar compounds, and except for tertiary amines can form intermolecular hydrogen bonding. Now, the question arises, why tertiary amine cannot form intermolecular hydrogen bond? The reason is, if you look at the structure of tertiary amine, you will find that there is no nitrogen hydrogen, there is no hydrogen attached to nitrogen. All the 3 hydrogens of ammonia are replaced by alkyl group, and if there is no NH bond, there is no possibility of hydrogen bond. As a result, amines have higher boiling points than the non-polar compound of similar molecular masses. Alcohols of similar molecular masses having higher polarity than amines have higher boiling points than amines. Here you can see, with the help of example, I will show you that this is ethane, this is methanol, and this is methanamine. The molecular mass of all these 3 molecules is almost similar, that is ethane has 30 molecular mass, whereas methanol 32 and that of methanamine is 31. But if you look at the boiling points of the three molecules, you will find that the molecule of ethane is much less as compared to that of methanamine, and boiling point of methanamine is much less as compared to that of methanol. So, the higher boiling point of methanol and methanamine as compared to ethane is because of the polarity of OH bond and NH bond. Similar is the case of normal propane, ethanol and ethanamine. All the three have almost similar molecular masses, but they have wide difference in their boiling points. Amines have lower boiling point than alcohols or carboxylic acid of comparable molecular masses. This is because the OH bond is more polar than the NH bond, and thus hydrogen bonds are stronger in case of alcohol and carboxylic acid than in case of amines. Here you can see that this is the hydrogen bond formed between a primary amine. Here hydrogen bond formed between different molecules of alcohols. Earlier we had discussed the boiling point of alkanes, alcohols and amines. Now we are going to compare the boiling point of primary, secondary and tertiary amines. Amongst the isomeric amines, tertiary amines show no hydrogen bonding and have lowest boiling points. Primary amines have highest boiling point due to a more extensive hydrogen bonding, and chain branching also reduces boiling points by 10 to 15 degrees centigrade. Here if we compare the boiling point of primary, secondary and tertiary amine, you can see that this is a normal propanamine, this is N-methyl ethanamine, this is isopropylamine and this is tertiary butylamine. Tertiary amine, secondary amine, and this is a primary amine. So, out of the 4 amines you can see that if we look at their boiling points, you find that tertiary amines have lowest boiling point, and the reason is that they cannot have hydrogen bond. The molecules of tertiary amines do not have association, and that is why they boil at a lower temperature as compared to their primary or secondary counterparts. You can see here a hydrogen bonding has been shown in primary amine and hydrogen bonding here has been shown in secondary amine. In case of primary amine, you already know that nitrogen is attached to 2 hydrogens. So, it can form hydrogen bond from both the hydrogen points, and there can be this kind of hydrogen bonding possible. Whereas, in secondary amine, the hydrogen bond is possible only with this NH bond. Reason is that there is only one hydrogen. So, secondary amines have higher boiling point compared to tertiary amines, whereas they have lower boiling point as compared to primary amines. We will now discuss the solubility of amines. All the 3 classes of amines are capable of forming hydrogen bond with water. I told you earlier that tertiary amines do not form hydrogen bond, but with their own molecules, but they can form hydrogen bond with water. The reason is the lone pair of electron is present on nitrogen or in case of tertiary amine also. So, all the 3 classes of amines are capable of forming hydrogen bond with water. As a result, amines of lower molecular masses up to 6 carbon atoms are soluble in water due to hydrogen bonding. With an increase in molecular mass, the solubility in water decreases. The higher amines are soluble in non-polar and mildly polar solvents like benzene, ether and alcohols. Here is shown the hydrogen bonding of amine with that of water. Now, we will discuss salts of amines. Amines form quaternary ammonium salt when treated with aqueous mineral acids or carboxylic acids. Amine salts are soluble in water. We have already discussed this reaction in the earlier slide also, that all the 3 classes of amines react with acid and form soluble quaternary ammonium salts. Now, we will discuss the structure of amine. If you look at the lowest or the first amine, that is methanamine, you will find that it has a structure CH3NH2, that is the nitrogen in amine is sp3 hybridized and has a tetrahedral structure. The 3 of the sp3 hybrid orbitals of nitrogen overlap with s orbital of hydrogen or sp3 hybridized orbital of carbon. The fourth orbital is occupied by a lone pair of electrons, and that is why amines like ammonia are pyramidal in shape. You can see here that this is nitrogen. This is an example of tertiary amine, you can see, where the nitrogen is tetrahedral in nature, is sp3 hybridized and has 4 sp3 hybrid orbitals. Out of the 4 sp3 hybrid orbital, one is occupied by lone pair of electron, whereas the other 3 have formed sigma bond by the overlap with sp3 hybrid orbitals of alkyl groups. This is the ball and stick model of amine. The carbon-nitrogen carbon bond angle in trimethylamine is 108 degrees, which is a mild deviation from the normal tetrahedral angle. Can you think any reason behind it? Why there is a deviation from 109.5 degrees? The reason is the presence of lone pair of electrons. The lone pair bond pair repulsion is more than bond pair repulsion. As a result, there is mild deviation from the normal tetrahedral angle in case of trimethylamine. Also, it has been found that carbon-nitrogen bond length is 1.47 angstrom unit, which is lesser than the carbon-carbon bond length in alkanes, which is 1.54 angstrom unit. Stereochemistry of amines. Now, when we say stereochemistry of amines, I think you can recollect that we are trying to discuss the molecules or structure of amines in the 3 dimension, and it has been found that since the nitrogen is, if it is appropriately substituted, then amines can show optical activity. Now, when we say appropriately substituted, what does it mean? If we take an example of a primary amine, then what will happen? Then there will be a nitrogen function with an alkyl group, a lone pair of electron, but 2 of the substitutions will be of hydrogen. So, if we look at primary amine, it will not show optical activity at all. The reason is that the 2 substitutions are similar, and that is why they will form a superimposable mirror image. Whereas, if in appropriately substituted secondary amine, like in this case is taken, that is one substitution is a hydrogen and other 2 are different alkyl groups, then this molecule forms a non-superimposable mirror image. And if the non-superimposable mirror image is formed, then we say that the molecule can show optical activity. There is generation of a stereogenic center in the secondary amine molecule. A secondary amine in which nitrogen is attached to 3 different groups is non-superimposable on its mirror image. Therefore, it is chiral in nature and exists in 2 enantiomeric forms, each of which, if separated from the other, is expected to show optical activity. But the case is different. What is different? That the molecule does not show optical activity, even though it has 2 different substitution. This nitrogen function, here you can see that this is a secondary amine. All the 4 groups, a lone pair of electron, 2 different alkyl groups and a hydrogen, all the 4 are different. Even then, the molecule does not show optical activity. And the reason behind it is that the energy barrier between the 2 pyramidal forms, this is pyramidal form, the energy barrier between the 2 pyramidal arrangements about the nitrogen is so low that they are rapidly interconverted. That is, this is one pyramidal form and this is another pyramidal form, and they keep on interconverting. As a result, it is not possible to isolate them, and if we are not able to isolate them, it is not possible to identify them as separate or different isomers. And that is why secondary amine or tertiary amines, even though having appropriate substitution, even though having a stereogenic center, does not show optical activity. This is very similar to the rapid rotation about carbon-carbon single bond which prevents the isolation of conformational enantiomers. Like in this particular case, you can see that this is a tertiary amine appropriately substituted, having a stereogenic center, but cannot be isolated because of rapid interconversion. Here this is the conformational isomer where conformers are not able to be isolated because of the continuous rotation along the carbon-carbon bond. Therefore, the unshared pair of electrons on nitrogen do not serve as fourth group to display optical activity in case of amines. The quaternary ammonium salts with 4 different groups show chirality. The reason is that there is no non-bonded electron pair on the nitrogen atom, and therefore, there is no interconversion possible amongst the 2 different isomers. Quaternary ammonium salts have been found to exist as configurational enantiomers. As you can see here in this particular case, this is a quaternary ammonium salt and its mirror image is non-superimposable. The reason here is that the nitrogen is not attached to any lone pair of electron. As a result, there is no possibility of interconversion of the 2 isomers. They are isolable, and that is why the quaternary ammonium salts show optical activity. Now, in primary amines, we have told you that chirality along nitrogen is not possible. The reason we have already told you that in primary amine, nitrogen is attached to 2 hydrogen atoms. If 2 groups are similar, there is no possibility of stereogenic center. In case of secondary and tertiary amines, chirality along nitrogen is possible, but the 2 isomers are not isolable because of the interconversion of pyramidal structure. But if we look at this molecule, this is an example of primary amine. Here you can see this is a primary amine and this molecule shows optical activity. Now, here we have told you that primary amines do not show optical activity. Here I am saying that primary amines are showing optical activity. Look at the difference. Here the amino group is attached to carbon which is optically active or which is chiral or which is attached to 4 different groups. This carbon is attached to 1 methyl, 1 ethyl, 1 hydrogen and 1 amino group. So, this is, even though it is a primary amine, the chirality is due to carbon function and not due to nitrogen function. So, primary amines do not show optical activity along nitrogen, but primary amines can show optical activity along the carbon present next to amino group. Amines in which rotation of or movement of nitrogen is restricted in such a way that its enantiomers cannot be interconverted or have a rigid structure show optical activity. Here show you a very interesting example of a tertiary amine. This is 1,2,2-trimethyl aziridine. You can see that this molecule, this is a heterocyclic molecule where nitrogen is a function of 3-membered ring and this nitrogen is attached to a methyl group and there is a lone pair of electron on nitrogen. But because of 3-membered ring along nitrogen, 3-membered ring gives a rigid structure to the molecule. As a result, the mirror image of this isomer is non-superimposable and that is why the molecule can be isolated as R and S isomer. Or in other words, we can say that even though a tertiary amine, as we have told you in earlier slide, that tertiary amines form pyramidal structure and that is why they interconvert and that is why they do not show optical activity. But in certain cases where rigidity is achieved in the molecule because of structure, then they too can show optical activity. Another very interesting example is of Kroger's base which is an organic compound that exhibit optical activity due to the presence of 2 bridgehead stereogenic nitrogen atoms as shown in this molecule. See, this is a nitrogen atom here and this is a nitrogen atom. Both of them are attached through a methylene group. So, they are forming a bridgehead nitrogen. Both the nitrogens are tertiary in nature and then they make a rigid structure. This structure is non-superimposable on its mirror image, and that is why the molecule shows optical activity. So, this is possible due to the rigid structure of the molecule. This is an exception where resolution of the two mirror image isomers is possible. So, to summarize today's lecture, we have introduced amines, we have given the classification of amines, we have discussed various classes of amines like primary, secondary and tertiary amine or quaternary amine or aryl alkyl amine or heterocyclic amines for that matter. Like we have also discussed aromatic amines here, and then we have discussed biologically active amines, we have discussed nomenclature of different classes of amines in detail, the salts of amines also we have discussed. After that, the properties of amines because of the polar nature of nitrogen hydrogen bond have also been discussed, where the amines show higher boiling point or higher solubility than corresponding non-polar compounds like alkanes. We have discussed the structure and stereochemistry of amines. We have discussed the stereochemistry of secondary and tertiary amines, appropriately substituted secondary and tertiary amines, the quaternary ammonium compounds also. And then in the next episode of organic nitrogen compounds, we will discuss some properties of amines. We will emphasize in the next lecture on basicity of amines, under what conditions the basicity of amines is reduced or enhanced, that we will discuss in the next lecture. Thank you very much.